Hello everyone, my name is Dr. T.S. Kurne in Department of Statistics, Rajarshi Chhatrapati Shahu College, Kolhapur. Today we discuss the first design, completely randomized design. This is a simple design of all the designs. In these designs, we have used two principles, replications and randomization. The principles of local control is not implemented in this design. Therefore, use of design is restricted to uniform experimental area. If the area is heterogeneous, the completely randomized design cannot be used. If the experimental area is homogeneous, then and then only here we have used completely randomized design. In other words, these designs should not used for the experiments having heterogeneous experimental material. Hence, in laboratory experiments in CRD is widely used in this design. Suppose we have V treatments and ith treatment being replicated Ri times. Means if we have 5 treatments and each treatment has replicated in different times, like I is equals to 1 to V, then the whole experimental area is divided into, for example, whole experimental area is N, then it is summation of Ri, I varies from 1 to V, or which is also equal to I varies from, for example, 1 to 4 Ri, means each treatment is replicated at 4 times. Now allocate all the treatment over the experimental area at random as per their expectations. This will provide you a layout of CRD. The ith treatments replicated Ri number of times, hence principle of replications is implemented in this design. Further, all treatments are allocated randomly, hence principle of randomization implemented. Means here though two principles are implemented. Suppose in field experiment there are 4 fertilizers A, B, C, D. That are means there are 4 treatments A, B, C, D, and we have to check whether which of the treatment of or fertilizers gives the maximum yield. For the purpose we have used CRD, then the treatment A, B, C, D replicated 3, 2, 4, 3 times respectively. Means A treatments replicated 3 times, B treatments 2 times, C 4 times and D 3 times. Then the layout of CRD is given as a below. This is the layout of design. Total 12 experimental unit. What is the application of this design? So CRD is mostly used in laboratory technique and methodological studies. For example, in physics, chemistry and biological experiments, some greenhouse studies, except in such type of experiments are experimental materials are homogeneous. Then next, mathematical model of this CRD design. Suppose we have V treatments and ith treatments replicated Ri number of times, then the mathematical model of CRD is Yij is equals to mu plus alpha I plus epsilon ij, where I varies from 1 to V, this is for treatment, j varies from 1 to Ri, this is for replication, where V is the number of treatments, Yij is the yield or responses due to the jth replications and ith treatment, mu is the general mean effect, alpha I is the effect due to ith treatment and epsilon ij is the random effect due to the chance. What is the assumption of this model? The observations Yij are independent and normally distributed with mean mu ij and variance sigma I square, and the treatments and error effect are additive in nature, means summation of double summation epsilon ij is equals to 0, where I varies from 1 to v and j varies from rij. Epsilon ij is equals to 0 and epsilon ij are identically independent, distributed with normally distributed with mean 0 and variance sigma e square. This is your assumptions. Now in CRD there are terms like sum of squares. So there are three sum of squares in these designs: total sum of squares, error sum of squares and treatment sum of squares. So splitting of total sum of squares is like that. Total sum of squares it noted as S t square, capital S square, which is equals to double summation of Yij minus y double dot bar square. This is your original formula of total sum of square. Here n is equals to summation of Ri, and double summation of Yij means it is a grand total. It is noted as y double dot or g, grand total of all observations. Or from that grand total we have to calculate total mean. This is noted as y double dot bar. So formula is this double summation and divided by n. So y double dot bar divided by n. So this is the y dot bar formula. Then next is, if the observations are sum over the replicates, then this is the treatment total. Sum over the replicates, this is the treatment total, means first treatment over the all replicates. T1 is treatment of first treatment, total of first treatment over all replicates, like the total response of all units receiving ith treatment. Similarly, from the total mean, this is the also treatment mean. So treatment mean is yi dot bar, it is total and divided by Ri, then we get the treatment mean. So this is the mean response of all units receiving the ith treatment. So total sum of square is equals to S t square double summation Yij y dot double bar. This splitting is, we have in this term we have to minus and plus the term yi dot bar term. First it is minus and then it is plus, so it cancel out, so remains as it is. So after that we split these two parts separately, means we consider this part as a and this part as a b. So the formula of a plus b bracket square is a square plus 2ab plus b square, and summation is entered here. So double summation a square 2 double summation a and b plus double summation b square, and this term gets simplified. First term as it is remains as it is. In second term we enter this j at here and I is here, and in last term we have j is over summation j over 1 to Ri is Ri, and this terminology remains same because in this term there is a no terms of for j. So we sum over j is quantity is Ri here. So simplification, we get this term as it is, this simplification or this summation is get entered, we get this term summation of Yij over j is yi dot and enter here not term j, so it is Ri into yi dot bar plus this term as it is. So if summation over I Yij, this term separate and this term separate, if simplifies this term, then this is yi dot bar, means it is yi dot divided by Ri, then Ri get cancelled, here remains only yi dot minus yi dot get cancel, so this term is 0, so this whole term makes as 0. So remains only quantity double summation Yij minus yi dot bar square, or another quantity is summation over I Ri yi dot bar square. So this terminology is total sum of square is the first quantity and this second quantity. So, first quantity for sum of square due to the error and this next quantity is sum of square due to the treatment. So, total sum of square is split into sum of square due to the error and sum of square due to the treatment. Now, next is the degrees of freedom. This is the sum of square. For the calculation of mean sum of square, we require degrees of freedom. So, how to calculate the degrees of freedom? For total sum of square, the sum of square, there are n observations in the form of yij and yi dot bar. However, there is a one constraint. Which constraint? Double summation yij y dot bar is equal to 0. In this case, total sum of square, there will be n observations, but there is a one constraint as defined above, and then the total independent variable becomes n minus 1, and which is the degrees of freedom of sum of square. So, degrees of freedom for the total sum of square is n minus 1. Similarly, for the computation of sum of square due to the error, we require n observations of the type yij minus yi dot bar. However, there is a v constraint in the form of double summation over j yij minus yi dot bar is equals to 0. I varies from 1 to v. Then the total number of independent observation for calculating the sum of square due to the error becomes n minus v. Here the n minus v. Therefore, the degrees of freedom for means sum of square due to the error is n minus v. Now, sum of square due to the treatment, the formula is this: summation over ri yi dot bar minus yi dot bar bracket square, and in this computation of sum of square due to the treatment, we require v observations of the type yi dot bar minus y dot bar, and however there is a one constraint of the type summation over yi dot bar minus y dot bar is equal to 0. Therefore, the number on the independent observation is v minus 1. Therefore, the degrees of freedom for the treatment sum of square is v minus 1. Therefore, the degrees of freedom for sum of square total is equal to degrees of freedom for the sum of square due to the error plus degrees of freedom for the sum of square due to the treatment. So, n minus 1 is this is the degrees of freedom for total, this is the degrees of freedom for error, and this is the degrees of freedom for treatment. Therefore, the degrees of freedom are additive in nature. The next calculation is the mean sum of square. Mean sum of square means sum of square divided by its degrees of freedom. So, calculate mean sum of square for the treatment is sum of square divided by its degrees of freedom, and the notation is small s square. So, this is the mean sum of square due to the treatment is sum of square divided by v minus 1. So, mean sum of square due to the error is similarly small s square is equals to sum of square due to the error divided by its degrees of freedom. Thank you.